Okay, so an amusement park ride called the gravitron. Riders stand backs against the interior surface of a cylindrical drum with a radius of 5 meters. So this is 5 meters here. The ride begins to spin until the riders feel stuck to the wall. The floor drops out from under the riders. So I don't know if you've ever been on this ride. You spin super fast, and you're stuck against the wall. And when the floor drops out, you're still stuck to the wall there. Assume the coefficient of friction between the rider's clothing and the wall is 0.4. Okay, and this is... Now draw a free body diagram of the rider. So let's look at this. I have a picture here. So let's draw the free body diagram. So I have gravity, downward. What else is touching him? Is the wall is here. The wall exerts a normal force perpendicular to the surface. Right? That's the rule. Normal forces are not up. Normal forces, the rule is perpendicular to the surface. Okay, now why doesn't he slide down? He's not going to slide down. He's like stuck to the wall here. So something's keeping him up, and that's going to be friction, static friction. If he doesn't slide down at all, okay, then frictional force, like the way you think of it is there's going to be static friction, first of all, because they're not rubbing against the surface, right? So static friction. And how do we know the direction? Well, a couple things. One, something's got to keep him up. So that's one way to think about it. But the other way is if there were no friction, he would slide down the wall. Like if I oiled it down, the wall is completely covered in oil and it's super slippery, he would still slide down the wall. Okay, so the static friction is going to oppose that by pushing him up. Okay, so that's our free body diagram. And it's static friction. This is important to understand, static friction. Okay, so now we're going to do the x and y components here. Okay, set up by Newton's laws. Let's say right is positive, we'll say up is positive. We do have to identify the acceleration, and the acceleration is 0 vertically, but there is an acceleration directed towards the center of the circle, centripetal acceleration, right? So AC is equal to v squared over r, and that's in this direction. Okay. So in the x direction, we only have one force. The normal force equals m times v squared over r, the centripetal acceleration. And in the y direction, force of friction is positive upward minus mg equals 0. Why 0? Because vertically there's no acceleration. The acceleration is only directed towards the center of the circle here. So those are our equations there. This and this. Now, what is the maximum period of rotation that will keep the rider stuck to the wall? Okay, so this is about the period of rotation, right? Remember we talked about one of the equations. The speed is 2 pi r over t, and we can rearrange that to be t is equal to 2 pi r over v if you wanted to do that. So what happens if the period's really big, then that means the velocity is really small. So let's talk about like what's happening here, right? In order to keep him from sliding to the wall, from sliding down, the frictional force has to equal mg. Now, what happens if the frictional force is not big enough, then like we're going to overcome the static friction and then we're going to start to slide. Okay, that's the thing, is that once we hit maximum static friction, we're going to begin sliding down the wall, right? Like if the friction I need is not enough. So how is the frictional force changing? Is you got to look at the normal force. If we increase, if the period of rotation is longer, that means he's going to go slower, okay? So if the v is smaller, the normal force is smaller. And then the FF max being equals mu Fn, if the normal force is smaller, then the maximum static frictional force is smaller. And if the maximum static frictional force is smaller, then that means it's going to go so small that it's going to, the mg is going to be greater than the frictional force, and then it's going to slide down. Okay, so a couple of things we have to identify. One, in this instance, for maximum t, that implies the frictional force has to equal the maximum frictional force, which equals mu times Fn. Okay, so then we're going to put that into our equation here. So we're going to say mu Fn has to equal mg, and then the Fn is mv squared over r. So then the m's cancel. And you can solve for v, by the way, is going to equal rg over mu square root. Okay, so let's calculate what that v is. That's going to be, what's the radius? The radius is 5 meters. and the mu is 0.4. They told us the coefficient of static friction was that. All right, so that's going to be square root 5 times 9.8 divided by 0.4. That's 11.07 meters per second. Okay, so we're going to take that and then solve for t. Now, t is 2 pi r over v. Why is this? Remember this formula? This is one of our beginning formulas. I think it's in the note packet, right? So it's the speed is distance over time. Distance around the circle divided by the period. And so you just rearrange. This is 2 pi times the radius, which was 5, and then divided by this 11.07. And that is 2.84 seconds. Okay?